Hi, my name is Despoina. I am a PhD student at the University of Western Macedonia, and I'm going to present you a research titled Digital Twin Modeling for Photovoltaic Systems based on deep learning. So, according to the International Energy Agency, the solar power capacity additions in 2021 were almost 150 gigawatts, which was higher compared to 2020. Now, the PV system installations is a considerable investment. So, in order to ensure the PV system viability and prevent the extensive power losses due to unexpected faults, the monitoring of the PV systems and the analysis of the recorded data are essential. One way to analyze the recorded data is the development of digital twins. So the digital twins simulate the PV power output considering the operating conditions, solar radiance and panel's temperature. So after we obtain the simulated PV power, we compare the simulated and the recorded PV power, we get their deviation, and in this way we can detect any anomalies in the PV power production. There are two ways in order to develop the digital twins. The first way is the physical based digital twins, and the other way is the data-driven approaches. The former refers mainly to the equivalent circuits, and in physical based models we have to define several unknown parameters such as the photocurrent, the series resistance, etc. And also, in order to develop the physical-based models, we need to know the PV system structure, how many inverters, how many strings per inverter, etc. Now, these limitations we can overcome these limitations by the data-driven approaches. So, this approach is based on artificial intelligence, machine learning, and deep learning. So we deal with the known parameters, and also we do not require the PV system structure. So the scope of this work is the development of physical-based digital twins, the development of data-driven digital twins, the comparison between the physical and the data-driven approaches, and finally, we propose a hybrid ensemble data-driven digital twin. Now, the physical-based model is actually based on the single diode model, and here we have the equation. Single diode model has been extensively used due to its simplicity. And in the single diode model, we have 5 unknown parameters: the photocurrent, the reserve saturation current of the diode, the diode ideality factor, the series resistance, and the parallel resistance. These parameters have been obtained from the PVSys library. So the scope of this work is not to develop a model in order to define the parameters, but to compare data-driven and physical-based approaches. For the development of data-driven approaches, we have used 2 machine learning models, the random forest regression and the support vector regression. We also used 2 deep learning models, the feed-forward neural network and the long short-term memory model. And finally, based on the efficiency of these models, we propose a hybrid ensemble feed-forward neural network LSTM model. The data that we have used at the present study are obtained from a PV system located in the southern Greece. The installed capacity of the system is 20 kilowatts, and the system consists of 3 inverters, 2 strings per inverter, and 15 panels per string. So we have also the structure that is required for the single diode model. Also, we have available data, the AC and the DC power per inverter, the solar radiance, the panel's temperature, and the data covers a period of more than 2 years. It has to be mentioned that the present analysis refers to the DC power output of 1 out of the 3 inverters. We additionally have formulated 2 scenarios regarding the selected inputs. The first scenario consists of the solar radiance and the panel's temperature, which are the variables that we use as input to the models. And the second scenario, in the second scenario, we exclude the panel's temperature and we train the models only with the solar radiance. It should be noted that for the physical-based digital twin, only the first scenario has been considered. And in order to evaluate the efficiency of all of the models, of the developed models, we have used 3 well-known indexes: the mean absolute error, the normalized root mean square error, and the mean absolute range normalized error. Now let's move on to the results. Here we can see the mean absolute error of the models regarding the scenarios, the first and the second scenario. As we can see, in almost all cases, when we use the panel's temperature as input alongside with the solar radiation, we can increase the simulation accuracy of the models. The only exception is occurred at the random forest regression, but it's only a small deviation. And regarding the models, we can see that the highest simulation error is obtained when the support vector machine is utilized, since the mean absolute error exceeds the single diode model. And here we can see the reduction of the simulation error. Specifically at the figure, we illustrate the mean absolute error, the normalized root mean square error with the orange line, and the mean absolute range normalized error with the blue line. And we can conclude that the employment of random forest regression can decrease the error up to 62.31%. This figure, I have to mention, that refers only to the first scenario, not the second, since the second had highest simulation error. So now, when we employ the feed-forward neural network, we can increase more the forecasting accuracy. Since the simulation, we have a decrement up to almost 67%. Now, the employment of the proposed model, the hybrid ensemble one, has the highest error decrement, which is up to 74%. But its efficiency is comparable to the standalone LSTM. And to conclude, at the present paper, we propose the development of physical models and data-driven approaches for digital twins in order to simulate the PV power output. The physical model is based on a single diode model, while the data-driven approaches, we utilized 4 different machine learning and deep learning techniques. And finally, considering the simulation error of the data-driven approaches, we proposed a hybrid ensemble feed-forward neural network LSTM model. All the data-driven models are tested on 2 scenarios regarding the selected inputs. And based on the results, we can conclude that the utilization of both solar radiance and panel's temperature can increase the simulation accuracy. Additionally, the employment of support vector regression can significantly increase the forecasting, the simulation error, and it has the lowest performance. And finally, the highest simulation accuracy is achieved by the proposed model. However, its accuracy is still comparable to the standalone LSTM. Thank you. If you have any questions.